Hello, and welcome to the lecture for Chapter S1, which is Supplemental 1. The title of this supplemental chapter is Celestial Timekeeping and Navigation. In the three sections of this chapter, we are going to talk about more details of the sky, how and why we see things the way we do in our sky when we look up at the planets and the stars, and the moon in particular. Then we're also going to discuss how we can use our latitude to find where we are on Earth. All right, so latitude and navigation. I should really say how we can find stars in the sky to then find our latitude and thus know where we are. All right, so it's the idea of using the stars to navigate, something people have been doing for hundreds of years, which does take us to our last section, which will be a little bit about the history of celestial navigation. All right, well, let's get to it. Celestial timekeeping and navigation. So in the first section, we'll talk about astronomical time periods. Now, I said we're going to learn more about motion of things in the sky. Well, that's because relative motion of objects affects time periods. You'll see what I mean. So our goals for this section are to ask, how do we define the day, month, year, and planetary periods? Okay, because we might take it for granted that there's a certain length of all these quantities, but why and how? And maybe there's more to it than we thought. We also are going to ask, how do we tell the time of day, and when and why do we have leap years? A very interesting question. Okay, so when you look up at the sky, there are certain things that you see. These are terms that we have discussed in a previous chapter. In your local sky, daytime or nighttime, directly overhead is the zenith. There is the horizon, which goes around the ground. And there is the path of the sun through the sky, known as the ecliptic. And that right there is also the celestial equator. Okay? So the ecliptic path shown here as the path of the sun, all right, clearly shown as little stars going in a circle through your observational sky, called the celestial equator. Okay? So the path that the star is taking. Okay? We also have a path of another star shown here, another loop. And we have the north celestial pole. Okay? So that is the terminology that we are looking at here. Okay? Now, there's a difference, however, between a solar day and a sidereal day. Okay? So let's look at some of the details here. If you measure the time from when the sun crosses the meridian today until it crosses again tomorrow, that's a solar day. So that's having a point where the sun returns to the exact same location in your local sky to where it started. All right? And that's probably what we think of when we think of a day. Think about, you see the sun rising, and then one day later, there's the sun rising again. Okay? So obviously the sun rises at different times each day, right? We have a variation in the length of the day due to the axial tilt, as we discussed in a previous chapter. But there's more to this idea of a day and the sun rising being synchronized. Because if you think about it, well, to wait for the sun to be in the same position in the sky one day later, a solar day, well, that is not the same as the Earth completing one rotation. But why not? Why not? All right? Well, here, if we go back to the sidereal day, we can see that sidereal day is 23 hours and 56 minutes, whereas the solar day is what you would expect, 24 hours. It is defined as 24 hours. Okay? So why the difference? The difference of a few minutes? Well, because in this case, the star or the sun, I guess in this case it's maybe shown as more of a star going around this. I kind of noticed here that this is not shown as the sun, right? It looks more like a star. I said, oh, there's clearly the sun, but it's, it doesn't look like a sun, where of course here a ball does. All right. Well, to return to that same point for the sun and to return to the same point for a star, that's not the same phenomenon. It's not the same process, okay? And by the way, having the sun move here on the celestial equator is not completely accurate because if you remember, due to the axial tilt, the sun doesn't move along the celestial equator. No matter where you are on Earth, the sun always moves away, slightly away from the celestial equator precisely because of that axial tilt. But regardless, it's for simplification, it's showing the same as for this hypothetical star that could certainly there are plenty of stars that do exist on the celestial equator. Because remember, the celestial equator is just a projection of Earth's equator. It's just a convenient way of splitting up what we can see in the sky. Now, still, we're talking about this difference between the sidereal day and the solar day. To summarize, the sidereal day is the time for a star to return to the same position in the local sky, and the solar day is the time for the sun to return to the same position in the sky, in your local sky. But why are they slightly different? Why should stars take slightly less time? Well, that's because stars are so far away that we only have to have the Earth complete one rotation, and then we're looking back in that same direction to that fixed background of stars, effectively fixed because they're so far away. But the sun's a different story. Because in order for us to be looking exactly at the sun in the same way, which would achieve it being located in the same point in our local sky, well, we have to turn a little bit more. We have to turn 4 minutes more in order to get that solar day completed. Because while the Earth was turning 24 hours to complete a rotation, what was it also doing? It was also orbiting. And that orbit means that it's not lined up in the same way as when the previous day started. So here's the difference between the two in writing. The sidereal day is the amount of time it takes the Earth to spin once with respect to distant stars. The solar day is the amount of time it takes the Earth to spin once with respect to the sun. Again, that one's 24 hours. This one must be slightly shorter, so it's 23 hours and 56 minutes. Okay? That is the key idea. Star returning to the same position, sidereal. Sun returning to the same position, solar. Which one's longer? The solar day. Okay? Now, why is that? Why is it slightly longer? Well, let's visualize it here. Here is Earth completing a rotation. Somewhere far away, so far away that it doesn't effectively move relative to us, no parallax, we are on some point on the Earth represented as this individual's arm. Then that arm is going to turn just as the Earth turns, and it's going to take 24 hours to complete that turn. After, well, not quite 24 hours, but after one complete rotation, a sidereal day, right there, sidereal, it's going to be pointing in the same direction as the distant stars. Okay? And the distant stars there's nothing special about them being stars. They just are a proxy or a step in for the idea that this is the Earth's rotation relative to just some fixed backdrop. It's the Earth's rotation without worrying about anything else. It has, in one sidereal day, 23 hours and 56 minutes, completed a full turn. But notice that that full turn means that this person's arm is no longer pointing towards the sun as it started. You see, we have to turn a little bit more, 4 minutes more of rotation, to be pointing back at the sun, because now we have completed a solar day. Okay, so that extra bit is a solar day. The day that is, again, more relevant because the sun dictates so much of our lives. Okay, so we've gone back around looking at the sun. And that's because this person, as they rotated, shuffled to the side in an orbit around the table, holding whatever this is. And that's just like what our planet does. Because here is Earth rotating around in 24 hours, rotating on its own axis that passes through the center of the planet. And since 24 hours is, well, about 1/365th of a year, and there's about 360 degrees in a circle, well, there are defined exactly as 360 degrees in a circle, which is about as many days as there are in a year, it's a very good approximation to say that we move about 1 degree, 1/360th of a full orbit in the time that we have one day, one rotation. So that's why we have to have that extra turn, 1 degree worth of extra turn, or 1/365th of a day. So in fact, the 4 extra minutes that it takes to go from the sidereal day to the solar day is 1/365th of a day, which would be 24 hours. Okay, very interesting. And you can see here that since the 365 and the 360, the way we split up circles in degrees, they don't exactly match up. We can say that it works out to be about 361 degrees of rotation. So there's a good explanation of the difference between the solar and sidereal day. Okay, so what does that mean? What's the significance of that? Well, it just means that when we actually think about the rotation of Earth, it's not enough. We have to also remember that it's orbiting. It's just a good indication of how motion is complicated, and we often have to consider multiple aspects of motion. And as we were just talking about, rotation plus orbit. Same for, in this case, the moon and the period of the moon. Okay, we know that the moon goes through phases. We've talked about them before. We know that the month is about as long as it takes for the moon to go through phases. That's where the idea of a month comes from. But it turns out that that's only part of the story, because we need to think about the orbit of the moon as well as the orbit of Earth. Well, of course, around the sun. Okay, so let's look at the picture first. So just like we had to consider two aspects of motion to determine the difference between the solar and sidereal day, we need to consider two types of motion to consider the difference between the synodic month and the sidereal month. Now, the synodic month is also sometimes called the solar month, by the way. That's another name you may see sometimes, because it is the type of month that is set by the sun, in the same way that the solar day is set by the sun. So, what is the difference? Well, it's very similar to the difference between the sidereal day and the solar day, because in the time it takes for the moon to complete an orbit around Earth, Earth has moved about 30 degrees. A much more significant move than a day, because of course a month is much longer than a day. So now it's a bigger portion of the circle. And that means that by the time the moon has completed an orbit, which would be a sidereal month, because that orbit is relative to Earth, it doesn't care about the sun at all. All right, so that's the sidereal month. Really the true time it takes the moon to orbit around Earth. If you were considering the physics of orbit and balancing forces and velocities, then the value that you would need to use for the period of the orbit would be the sidereal value, the sidereal month, because that is the true orbit relative to the gravitational source, which is Earth. Now, again, that's great, but we care more about the phases of the moon. We think of a cycle of the moon being completed when we get back to, say, a new moon, right? Well, to get back to a new moon, if we started with a new moon, takes extra time than an orbit. It takes an extra 30 degrees worth of moon orbit around the Earth, because Earth has orbited around the sun, right? So we still need, just like before, we need that extra movement, right? And to cover that extra 30 degrees takes a few extra Earth days, because it's just a bigger orbital period. So adding a little extra makes a more substantial difference. So now, instead of just having a few minutes, which almost seemed insignificant, there's actually quite a few days of difference between the solar month or synodic month and the shorter sidereal month. Let's take a look on the previous slide. So the synodic month is the amount of time it takes the moon to repeat its phase, new to new. All right, this one is relative to the sun. This is a longer month, which is 29.5 days, and this is what people mean when they talk about a month. The sidereal month, however, is the time it takes the moon to orbit Earth, regardless of the sun. Okay, so the amount of time it takes the moon to complete one orbit with respect to the background stars, right? Or Earth for that matter, but again, it would making it relative to the background stars is also fine. And here we can see that it's over 2 days shorter. All right, so it takes 2 extra days to cover this distance here. So about 2 days for the moon to cover that distance. Okay. All right. There's also, if we're talking about years, a difference between a sidereal and tropical year. What's that? Well, as you can see, there's a trend here. The sidereal year is the amount of time it takes the Earth to orbit the sun once with respect to background stars, okay, which is just some fixed backdrop. The tropical year, on the other hand, is the amount of time it takes the Earth to go from the March equinox one year to the March equinox on the next year. Okay? So in general, right, and again, there's a slight difference here between the two, and that's going to be due to, if we're thinking in terms of the tilt, I believe this one shows up because of maybe a little bit of an elliptical orbit and getting back to that same exact, because the equinox is an event that is absolutely dependent on the alignment of our axial tilt with the ecliptic plane. And so to get that same alignment exact in the same place, the slightly off circle, slightly elliptical nature of our orbit is going to affect the two. But you're not responsible for an actual value difference, a number of days difference in this case. Okay. But in general, as you can see, the word sidereal, any sidereal period, is always measured relative to that concept of a fixed background of stars that don't move, okay? Whereas a synodic period is a period of a planet that is aligned with the sun in our sky and then similarly aligned, okay? So we saw that word, synodic, used for the moon. And again, you will see in some other textbooks that I've seen, they actually use the word solar, since it is, of course, directly tied in with the sun. Okay? But the word synodic maybe is a more traditional term. But regardless, we saw the moon had a synodic period. So would other observed planets in the sky, like Mars, other large bodies. The moon, of course, is not a planet. Mars, Venus, Mercury hard to see, but possible to see right at sunrise and sunset, especially sunrise. So that idea would be the synodic period of that planet. It's not its actual sidereal period, which would be its orbit relative to the background of stars. Instead, it's how we observe it from Earth, because both we're moving and that planet is moving, both of us orbiting around the sun. Okay, so as far as planetary periods go, and this idea that what we're going to observe from Earth is always going to be the synodic period, there's also some terminology about where that planet is located relative to the sun and relative to us. So these are kind of interesting terms, okay? So here we are on Earth, and when we look at other planets and perhaps considering one planet that's outside of our orbit, like Jupiter, shown twice here, and a planet that is inside of our orbit, closer to the sun, in this case, Venus, we can see we have some interesting terms. We have opposition. Opposition happens for any planet when it's on the other side of us from the sun, right? So it's directly away from the sun. There's a line between the sun, Earth, and that other planet. So only planets with orbits that are larger than Earth's, so Mars, Jupiter, Saturn, Uranus, and Neptune, they can have periods of opposition or moments of opposition. This is one time in our two relative orbits where this happens. With the planets that have orbital periods that take hundreds of Earth years or over 100 Earth years, like Neptune with some 140 Earth years, well, you can guess it takes a long time to get opposition, right? You have to wait for sometimes more than a human lifetime to have this event occur, okay? You can also have conjunction with these planets that have larger orbits than Earth. Now, for the inner planets, which are just Venus and Mercury, well, they have some more terminology. They have inferior conjunctions, which is where they're between us and the sun. This is the times where we could even see them passing in front of the sun, which doesn't always happen because our orbits are not lined up. there's a slight tilt between what is our, kind of, if you define the ecliptic plane as Earth's orbit around the sun, the other planets are 2 to 5 degrees off from that definition of the ecliptic plane. By the way, you can also have another definition of the ecliptic plane, which is actually the sun's orbital, radius, basically its equator, and that is not the same as what we call the ecliptic plane, basically the plane between, the plane of Earth's orbit around the sun. Point being is that the one we usually use is, from an Earth-centered point of view, not that we think the Earth is center of the solar system, but just we care more about Earth, that we use that definition for the ecliptic plane being the plane formed by Earth's orbit around the sun. Okay? But the idea is that there is some tilt between those, which means that it's unlikely, if, even when there is an inferior conjunction, that we actually see Venus directly on top of the sun. But every so often that happens. It happened just a few years ago with Mercury. Mercury actually passed in front of the sun, and it was a little dark dot that you could see with the right screen on your telescope moving over a few minutes across the sun. All right, and Venus will do that too, but it's also a very rare event. Okay, but the rest of the terminology, we also have the western and eastern elongations, okay? And the greatest elongations are going to be the points where you have the greatest length to basically that displacement, that line connecting Earth to that interior planet. And finally, we have the term superior conjunction, which is when a planet like Venus or Mercury is on the other side of the sun from us. Just recently, we had a conjunction with Mars on the other side of the sun from us, where NASA lost contact with all its Mars rovers because there's no way to send a signal through the sun in terms of a radio signal or such. But that would have been a conjunction, not a superior conjunction, because, just like it is with Jupiter, because Mars is, well, outside of our orbit. Okay? So only Mercury and Venus can have superior conjunctions. All right, here's an example of transit. This is showing Venus, which happened longer ago. I don't remember, the next time Venus is going to have a transit is going to be a while. That is the term for what I was referring to recently when Mercury had a transit. Mercury was quite a bit smaller, right? It was a smaller dot, but it was still quite dramatic to see it moving across the sun. So how do we tell the time of day? Well, this is a sundial, see? An ancient way of telling the time of day. So apparent solar time is defined as when noon is the time when the shadow of a sundial is shortest. Okay, so on that day, noon is that point. Okay, that's the apparent solar time. So you can set that day. That's the way people did it for, well, many human generations. On the other hand, mean solar time is where noon is set to the average time when the shadow on a sundial is shortest. It accounts for the subtle difference in day lengths. Okay, because there's going to be a change. Right? It's not going to be the same everywhere. Standard time is mean solar time in the center of your time zone. Okay, and you have to have a time zone because obviously not everybody experiences the same time all across Earth. Of course, it's nighttime for one side of the Earth and daytime for the other. But then there's also the concept of universal time, which is what people want to use and do use for working with satellites, right? Because you have to have some agreed upon time for them. And what time zone do you use? You have to all share the same time zone effectively because you're no longer on Earth. And it's been agreed that universal time is set at the prime meridian, which is the same time zone as Greenwich, England, which is just a historical artifact, definitely tied in with colonialization and the importance of England historically. So this is a useful standard for navigation and astronomy, the idea of universal time, UTC. Okay, here are the time zones of Earth, right, which are quite interesting. You can take a look at that. And now let's briefly talk about why we have leap years. And by the way, this is the path, this pretty picture, which is not terribly relevant to leap years, but it's still relevant to relative motion of objects in the sky. This shows a day probably right north of the Arctic Circle where the sun never sets. It takes a path where it dips down, but it never actually goes below the horizon. So then you have, well, the observed path of the sun in your local sky for anyone north of the Arctic Circle. They get at least one day out of the year that looks something like this. But back to leap years. Okay, so because there are 365.25 days in a year, it's not exactly 365, well, but we can't, that'd be weird to have a quarter day that we officially acknowledge every year. Instead, we stick with 365 days, acknowledging that every 4 years we've built up a total, 4 times 0.25, well, we've built up a total of 1 extra day. So once after 4 years, that 1 extra day has been accrued, well, then we acknowledge it as a leap year where there's 1 extra day and that day is allocated to February. Okay? Now, the Gregorian calendar, on the other hand, adds even more subtle corrections to stop the equinoxes from drifting. Because you remember that there's that difference between the tropical year and the sidereal year. And, well, the Gregorian calendar cares about that, and they don't want the equinox to ever be on a different day of the year, where it certainly is in the standard Julian calendar. For example, the March equinox is sometimes on the 21st, sometimes it's on the 20th. I think it's also possible for it to be on the 22nd, okay? Whereas the Gregorian calendar makes sure it's always on the 21st. So what have we learned in this first section? Well, we've learned about, or we've answered the question, how do we define the day, month, year, and planetary periods, right? We talked about all those differences between sidereal and solar, or sidereal and synodic. We also talked about how we tell time in terms of basing it off of noon and having standard time. And we briefly mentioned, which I think was just a complete story, that because the year is not exactly 365 days and it's closer to 0.25, well, then we can have a correction every 4 years and have 1 extra day on a leap year. And I guess that extra day you could call the leap day. All right, on to the second section. In this section, it's titled Celestial Coordinates and Motion in the Sky. Here, we're going to talk about how we can locate objects in the celestial sphere. Okay, so we've established this concept before, but we're just going to get some more details into it. The concept being the celestial sphere. We'll also talk about how do stars move through the local sky and how does the sun move through the sky. Okay, so we have our local sky, the terms zenith, meridian, horizon, which I started mentioning at the very beginning of this lecture. Here we have Earth. Earth has its equator, it's got its poles, okay, and it's got latitudes. It also has longitudes, which have no natural 0 point, like the equator is just naturally 0. It's a special point between the poles. But we define 0 longitude, as mentioned, as a particular line that goes through Greenwich in England, okay? That's just that one longitude line. The celestial sphere is split up in the exact same ways, but the terms do differ slightly. We have, instead of latitude and longitude, we have declination for latitude, and we have right ascension for longitude. Okay, same idea. Right ascension is measured relative to some line that goes around the around the poles, with a 0 set at the March equinox. How do you set the March equinox, a period of the year, as a point on a globe effectively? Well, remember, this globe is the celestial sphere, and the celestial sphere has the path of the sun in it. And so there's a certain point where the sun is on top of a particular constellation. The constellation remains fixed in the celestial sphere. So that means that any location of the sun, shown as yellow dots here, represents, well, precisely a day of the year, a time of the year. So it makes sense then to talk about right ascension relative to the March equinox. So in other words, a right ascension value is 0 at the March equinox. All right, and that's the equinoxes are a natural point for doing this, more so than Greenwich, England, because everybody on Earth experiences the equinox. On that one day, everyone has a day of the same length because the axial tilt is perpendicular to the direction of orbit. So it's not like the solstices where, one half of the Earth is experiencing very long days, when the northern half and the southern half is experiencing very short days, at least in the summer solstice. Okay. And also, as I mentioned before, do notice here, more accurately shown, the ecliptic is like a belt that is off angle from the celestial equator. And the fact that that is the case, the fact that the ecliptic, the path of the sun through the celestial sphere, is not lined up with the celestial equator is precisely because of Earth's axial tilt. This angle here is the 23.5 degrees of Earth's axial tilt. Okay, well, so a little bit more about the terminology with the celestial sphere. There are the celestial poles. There is the celestial equator. shown right here. Excuse me, shown right here. And we did see this terminology in a previous chapter. This is a review. There are the equinoxes and solstices. These are special points on the ecliptic, okay? Identifying these on the ecliptic, this is new. We did not see this before, right? So here is the September equinox, the fall equinox. There is the March equinox, and then December and June solstice. What do you see special about those points? Well, the equinoxes are when the sun crosses the celestial equator. In other words, when the ecliptic bisects the celestial equator. We have the two loops, okay? The solstices are when the ecliptic and the sun is furthest from the celestial equator, all right? At its maximum of 23.5 degrees, precisely the axial tilt, okay? So those are those four special points of the sun's path through the celestial sphere. And remember, this is not the local sky, okay? What you see in the sky depends on where you are on Earth. The celestial sphere is a concept that applies to the entire sky. So everyone on Earth can talk about the same celestial sphere, but not everyone on Earth has the same local sky, of course. More about celestial coordinates and more details about those terms I identified 2 slides ago, declination and right ascension. So declination is simply like latitude on the celestial sphere. It's got 0 at the celestial equator, just like latitude is 0 on Earth's equator, okay? Now, we don't use north and south, however. The terminology is positive and negative. So you either have positive declination or negative declination, okay? Positive going towards the north and negative going towards the south. But the terms are just used differently here, okay? Now, right ascension, I think, is similar enough to longitude, but as I said, it takes a little bit to get used to. The fact that it's relative to a time of the year, but we've seen that's just some point on the celestial sphere. Okay, so right ascension is longitude, and it is defined as 0 at the March equinox. Okay, which is just where the ecliptic crosses the celestial sphere or the celestial equator. Okay, so let's look at coordinates of some star, in this case, a very bright star, if you're able to see it in the sky, Vega. Now, Vega, because it's a star, remains fixed. It has a fixed value of declination and right ascension, always, okay? Now, very nearby stars move over many years because of the motion of stars in the galaxy, relative motion of stars, even stars that orbit each other. So, there's some motion. There's a tiny bit of parallax over a single year, but that's going to be measured in arc minutes and often more in arc seconds. So although there are tiny changes in terms of declination and ascension, they basically don't change at the integer level, at the fact that it has maybe a value of 38 and 18. That will never change, okay? The things that move substantially through the celestial sphere are the moon, the sun, and the planets, okay? But the stars don't. They stay fixed for most purposes, right? Unless you're trying to be very, very accurate. All right, so hopefully that makes sense. All stars in the celestial sphere have fixed values. You can look them up, okay? The sun moves around the celestial sphere, right? Because it's so much closer to us, our orbit makes its apparent location in the sky change dramatically, right? Of course it does, okay? So that means that, for example, if you are standing on, let's take a look here. So we've got the path in June. So let's see. So yeah, this is actually showing it through this is not a local sky. For some reason I was thinking this image was showing a local sky image, but it's not. It is showing of course, the celestial sphere. We've got the poles, all right? Here's the ecliptic, so the path throughout the year, okay? And then we can see that this circle right here, this declination of positive 23.5 degrees, that just shows where the sun is going to be located in the celestial sphere at the summer solstice, that highest point. All right. So here are some locations of the sun's approximate celestial coordinates at 1 month intervals. So starting with the March equinox, of course, it's going to be at 0 right ascension by definition, and it's also going to have 0 declination because the March equinox is the time where it passes across the celestial equator. So that means it must have a latitude of 0 degrees, which we call declination. Okay, so a month later, however, it has moved longitudinally, so it now has a right ascension of 2 hours, and it has a declination of 12 degrees, right? It's moving up away from the celestial equator as the days get longer. We move into March, and it's further off in the right ascension direction. It's even higher in terms of the declination, okay? So that means that anyone in the northern hemisphere would see it higher and higher in their local sky. We'll talk more about that in just a second. Finally, it's going to reach its highest point, or its highest declination in the celestial sphere on June 21st, because that's the solstice. Its longitude is now 6 hours, which makes sense. Okay, its right ascension is six hours, because it's going to be 24 hours to go all the way around. And I think that's something I need to pay some extra attention to, and want to make this clear for you, is that we do measure right ascension in hours, right, relative to that 0 point, that zero longitude, and it's 24 is the total amount to go all the way around. So the longitudes go from 0 up to 23.99 and then back to 0. So it's 24 is the total number of units to go all the way around in terms of longitudes. That's different than the way we do longitudes on Earth, because we just stick with the degrees. So longitudes relative to 0 at Greenwich, England, are measured in degrees. So they go from 0 back around to 360, or I guess they go to. They don't go. They probably go to 180 if I think about it in terms of longitudes. Let's see if we can go back and check, because we had that image. Yeah. So the longitudes 90, because okay, so they're yep. So we can see they 120 west. So they're split into 180. So longitudes are split between east and west. So the hemispheres decided by a line that goes through Greenwich, England, as I've said many times. And so we got 180 on one side, and then we got 180 on the other side, for a total of 360. Okay. So that's how we split up longitudes. Remember that latitudes are actually split up with 90 and 90, okay? Well, right ascensions are going to have that positive and negative, declinations will, but right ascensions have a total of 12 hours to go all the way around. So it's 12 hours instead of 360 degrees. That makes sense because it's based on the idea of a day. And so then 6 hours would be a quarter rotation, okay? So when we get here to this point that the June solstice, June 21st, relative to March 21st, is 6 hours or different of right ascension, makes sense because it's a quarter rotation difference. Okay, and on that same day, where the sun has a right ascension value of 6 hours, having started at 0 hours, it's going to have its largest declination, its latitude in the celestial sphere, of 23.5 degrees. Okay, and then we can continue on with it, throughout the year. As you can see here, a bunch of other points. Make sure this makes sense to you, right? Because this is so important. And the big idea here is that this is the position of the sun in the celestial sphere. All right, we're not talking about local skies, not yet, at least. Okay, so now let's do it. How do stars move through the local sky? Okay, well, let's start with a unlikely but good case in terms of logic. Let's consider someone standing on the North Pole, right? So there they are. That's the same person zoomed in and zoomed out, all right? So here we have them zoomed in, and this is looking at them as if you could see them standing on the Earth. Well, from their perspective, all stars will be what's called circumpolar. No stars will actually rise and set, okay? They're just going to appear to make circles around the sky. Some will circle right at the horizon and for all practical purposes being invisible. Many will circle at some angle higher than the horizon, and then they'll even have some, like the North Star, Polaris, that will almost stay fixed because it's so close to the North Celestial Pole, and it'll make a tight little circle, okay? But all the stars will be circumpolar. They're just all going to move in that direction, which is quite different than what you maybe expect being in a middle latitude, because you're used to stars rising and setting. Not so at the North Pole. Likewise, not so at the South Pole. Okay? So at the poles, North Pole being the example, the stars move parallel to the horizon. Okay, so in parallel circles with different radiuses, right? So, like I said, some circles tighter than others. A star's declination is equal to its altitude, because you're effectively looking at one half of the celestial sphere when you're at the North Pole. And since your horizon matches up with the celestial equator, there's an exact equality between the altitude in your local sky and the actual declination. All right, so I'll write over here, altitude equals declination. But that's only true for someone standing at the North Pole. There'll be a relationship between altitude and declination at any latitude, and we'll define that, but you have a very easy relationship between the two if you happen to be at the North Pole. They're equal to each other. Again, remember that altitude is a local sky term, and declination is latitude on the celestial sphere, or the equivalent of latitude. All right, so now let's look at another extreme case that helps illustrate the idea. What does the sky look like at the equator, particularly star movement? We're not talking about sun movement, we're talking about stars. Well, the stars at the equator look very different. None of them are circumpolar, they all rise and set. Because someone standing at the equator, they're dictated by the motion of Earth, and they're moving with a maximum circle, right? They're not getting rotated relative to the backdrop of stars, and so they're getting spun around it, okay? So the stars, in this case, move perpendicular instead of parallel to the horizon, and stars with a declination of 0 rise due east and set due west, because any star with a declination of 0 degrees is a star that's located on the celestial equator. Well, this person is located on Earth's equator, all right? They are on Earth's equator, so here's Earth, right, with its rotation axis, south and north pole. Our stick figure is right there on the equator, okay? So any star on the celestial sphere is directly overhead, rising exactly in the east, passing through the zenith, and setting in the west. Stars with a declination greater than 0 rise north of due east and set north of due west, like this one, for example, with a positive 30 degrees declination. If it has a negative declination, then it's going to rise south of due east and set south of due west, like this one right here with a negative 30. Okay? So that's what it looks like at the North Pole, as an example, and the equator. But what about normal latitudes, I guess, where most people live? Well, they're more complicated, but they fit between the two. So looking at the two extreme cases of a pole and the equator, hopefully we can make sense of this, all right? So stars at high declination will be circumpolar, okay? So stars that are near the north celestial pole, for people standing in the northern hemisphere of Earth, they will see those stars as circumpolar stars, like this one shown here with a declination of 60 degrees. But stars at a low declination will appear to rise and set. So stars that, say, have a declination of 0 degrees that are located on the celestial equator, for someone in the northern hemisphere at a middle latitude, they'll see a star like that rise, take a curved path through the star, and set, okay? So it won't rise, it won't follow a direct line. It won't go, straight through the zenith by any means, even if it rises from the due east. Because it would still be due east, because any star located with a declination of 0 degrees will always rise due east. But unlike for an observer located at Earth's equator, this observer located at a middle latitude in the northern hemisphere will see that star rising due east, but take a path where it will not pass through the zenith. Okay, that's a key difference. Okay, so now the sun, because we can make a lot of sense about the sun's path to the sky with the same understanding of the celestial sphere as compared to local skies. So the question is, how does the sun move through the local sky? Well, the daily motion of the sun is the same as any other object at the same declination. Okay, so if that sun, if it's the time of the year where the sun is exactly located on top of the constellation Leo, for example, then the stars in that constellation and the sun share that declination as well as that right ascension, and they're going to move in the identical way from the point of view of an observer on Earth. Of course they would, right? Because there's not that like our motion relative to the sun is not significant. We, as you know, we only move 1 degree in the time it takes us to rotate around our axis once. So the sun effectively remains motionless during the time that we complete that day. Now we know if we're doing the small correction between the solar day and the sidereal day, there is a tiny difference, but not enough to discuss here. Okay. However, over the course of the year, the sun's declination changes because, yeah, it certainly adds up over time. Okay, over the full year, rather than just one day, there's different locations that the sun is going to take. It's going to be at different points in the celestial sphere. unlike stars, the value of the sun, its right ascension and declination, vary. Of course, right? We've seen that. Okay. So then let's look at examples of different days in the year and the different paths that the sun will take. Okay? So this is someone standing at a middle latitude in the northern hemisphere, and they're going to see the sun on the longest day of the year, on the summer solstice, take a path through the sky where it's going to reach a maximum altitude in their local sky of 73.5 degrees. Now that 73.5 degrees is 23.5 degrees relative to the celestial equator, okay? So the celestial equator is located right here, right? And that is the exact point that the sun would reach on either the March or September equinox. So that means that the angular distance in your local sky between the highest point that the sun reaches and the point that it reaches at the either equinox will always be 23.5 degrees for anyone on Earth, okay? And on the shortest day of the year, the sun will only get to an angle of, of 26.5 degrees above the horizon. So that's an altitude of 26.5 degrees. That's because the sun will be lower than the equator by 23.5 degrees. And here's a question. What is the latitude of this person? Because we know we can think about the celestial sphere with its declination and its right ascension, but what is the actual latitude of this observer with their local sky shown? Well, we know it. It's 50 degrees. So this particular individual is standing at a latitude of 50 degrees. How do we know that? Because we know that on the equinox, the sun is at the celestial equator, and we know that the difference between where the celestial equator is relative to your zenith and horizon is the altitude above the horizon. Pretty neat idea. Okay, so let's talk about some special latitudes. Because the Earth's axis tilt is roughly 23.5 degrees, there are several quote-unquote special latitudes. Okay, well, at the North Pole, the sun circles the horizon on the equinoxes. The sun circles the sky at an altitude of 23.5 degrees at the summer solstice. That's as high as the sun ever gets, right? Which is pretty remarkable. You can think about that's why it's so cold at the poles. If that's the highest point the sun ever reaches, okay? And then on the parts of the year, the months of the year where the sun never rises at all, the sun is circling 23.5 degrees below the horizon for someone at the North Pole. And that would be, say, at December 21st. And it's going to be below the horizon for many days before and after December 21st. That's where it's this perpetual darkness at the poles, all right? And of course, it would just be the opposite at the South Pole with perpetual darkness around June 21st, okay? But we're going to get to those special latitudes, okay? The sun passes through the zenith, go back to the equator first. The sun passes through the zenith at noon or on noon of the equinoxes for anyone located at the equator. And the sun's path takes it furthest from the zenith on the solstices, where it's still going to, come rise up and you still have a very long day, right? The day length on the equator never changes. So the length of the day is always 24 hours. But the path of the sun does vary, so the directness of the sunlight varies over the year. So you would get more direct sun at the equinoxes for someone on the equator, and slightly less direct sun at either of the solstices. So in a sense, you could think of the solstices as being 2 times of the year where the weather would be, or the temperature, the intensity of the sun is slightly less. It's almost like someone at the equator has 2 tiny winters and warm the rest of the year. But the day length never changes. Okay, so that's stuff we kind of already talked about, but a good review. Now let's talk about those special latitudes, particularly the tropics and the Arctic Circle and the Antarctic Circle. Okay, so the Tropic of Cancer and the Tropic of Capricorn represent the northernmost and southernmost latitudes where the sun will pass directly overhead at some point during the year. So if you're located exactly at either of the tropics, you would have one day of the year where the sun reaches the zenith and you have sunlight coming directly overhead. Anyone that is going to be, closer to the equator than the tropics will have more than one day of the year where the sun reaches the zenith and is directly overhead. Well, I guess I could say that it will be closer. You'll have more days where the sun is higher, but you're still only going to have one day where it is exactly at the zenith, no matter where you are. But anywhere between the tropics, you'll have one day where it's exactly at the zenith, but then you'll have, it's if you're at the equator, as you know, you'll have many days where it's going to get very close. You'll have, if you're further from the equator and closer down one of the tropics, then it becomes colder. The paths become a little bit more elongated further away, which we can kind of even see here, right? So like the minimum angle at the tropic, let's say the Tropic of Cancer, so the northern one, the minimum angle that the sun is going to, or altitude that the sun will have relative to the horizon is 43 degrees, whereas at the equator, so you think hotter part of the Earth, it in fact is, because it's going to be about 66 and a half. Okay, so that's just 90 minus 23 and a half. So 66 and a half degrees is the lowest point that the sun gets, or the lowest altitude that the sun achieves at noon, right? So indeed, right, higher sun on average at the equator than the tropics, but everything between the tropics has one day where the sun passes through the zenith, okay? So that defines this part of the Earth, from the Tropic of Cancer to the Tropic of Capricorn, from the northern to the southern tropic, okay? So that's the tropics. Now the Arctics. So the Arctic and Antarctic circle represents the latitudes above the Arctic or below the Antarctic, where there will be more than 24 hours of consecutive sunlight during the summer and darkness during the winter. So in other words, in this case, we can really say you have at least one day where the sun never sets if you're above the Arctic Circle, and you have one day where the sun never rises if you're above the Arctic Circle. Likewise, if you're below the Antarctic Circle, okay? That's because you've reached a point where your latitude relative to the North Pole and your declination relative to the North Celestial Pole allow for the axial tilt to achieve a point where you either stare at the sun all day and all night, or you stare away from the sun all day and all night. All right. So let's look at an example of someone right at the Arctic Circle. All right. So this is in the northern hemisphere. This is not the North Pole anymore, although it still kind of looks like it with the igloo and everything. But it's not the North Pole. It's just in the Arctics. Right. You can tell it's not the North Pole because not everything is circumpolar. There is a tilt. So you can see for someone exactly at the Arctic Circle, the highest point that the sun reaches in the local sky, its highest altitude, is 47 degrees, and its lowest altitude is 0 degrees. So that means that on December 21st, it kisses the horizon, but never actually rises. On the other hand, on June 21st, for this person right at the Arctic Circle, the sun touches the horizon and almost sets, but never quite sets. Okay? So that means that on this day of the year, June 21st, it would be a day of perpetual light. So what have we learned in this second section? Well, we answered the question, how do we locate objects on the celestial sphere? We talked quite a bit about the idea of taking coordinates with declination, right, measured in positive and negative degrees from up to positive 90 degrees and down to negative 90 degrees, and right ascension, which goes from 0 hours to 24 hours, all right? So it goes all the way around the Earth. 0 hours passing through the March equinox. We also answered the question, how do stars move through the local sky? Stars move on paths dependent on their declination and the latitude of the observer, okay? That's why different stars are more easily observed or even possible to observe at different places on Earth, okay? Think about a star that has a declination of positive 90 degrees and at that point, any value of right ascension would be effectively the same, but let's give it a right ascension of 0. So if I have a star that has positive 90 degrees in terms of its declination, and then a value of 0 hours right ascension, well, that star is located at the celestial pole, the North Celestial Pole, and it would be completely invisible to anyone in the southern hemisphere. They simply would not be able to see it. And in fact, a star almost like that exists, the star Polaris, okay? And we also answered the question, how does the sun move through the local sky, right? Since we answered the question about stars moving through the local sky, we should have certainly focused on the sun. And we learned that just as stars do, though with a declination that changes throughout the year. Let's look at our final section here, which is quite a bit shorter. This is where we'll talk a little bit about the history of celestial navigation, as well as a little bit about determining your latitude and longitude for yourself. All right, so here we have an ancient picture of Amerigo Vespucci, all right, exploring with celestial navigation. So you can determine your latitude, pretty cool, If you can find the north or south celestial pole, such as Polaris, it is simple. The formula is altitude, that's a local sky term, equals your latitude. So if the altitude of Polaris is precisely equal to your latitude, all right? In the southern hemisphere, there isn't a star located at the north celestial pole, so you have to be a little bit more clever here. But if you can find something at that point, if you know to look, if you have a telescope and you know to look for something there, because there are stars that are invisible to the naked eye that are located at the the south celestial pole, then there you go. You have found your latitude. You can also determine your latitude from the altitude of any star or the sun as it crosses the meridian, all right? Because then you know, you can look it up and you can say, oh, on this particular day, think the sun, for example, right? You know, like we talked about this idea quite a bit, so let's go back, right? Let's look at this person on the Tropic of Cancer. Well, they know on a particular day, say on December 21st, that the sun is going to reach at a latitude of, what was this one? This one was the Tropic of Cancer. Oh, so 23 and a half degrees above the equator. Well, on that particular day of December 21st, they know the sun, when it crosses the meridian, all right? The part of all these local sky figures that I haven't mentioned as much as the zenith and horizon, but it's a line that connects the north and south poles, okay? Or the north direction and south direction of your local sky. So the sun, when it crosses the meridian, if it crosses at an angle or at an altitude of 43 degrees, that's what you would observe as maybe a lost person in the ocean. You make that measurement. You say, okay, I waited for to cross the meridian. I used my compass to know exactly where the meridian is, and I noticed that the sun crossed, and I measured that angle, and I measured 43 degrees above the horizon. That tells you that you are located exactly at 23 and a half degrees north of Earth's equator. In other words, exactly at the Tropic of Cancer. And if you've got a different number, it'll tell you you're located somewhere else. Okay? So that's the idea, that you can use the sun as it crosses the meridian. All right? What about your longitude? Right? Well, you can determine your longitude, or rather, to determine your longitude, you need to know both the apparent solar time and the time at some other known longitude. Okay? So in practice, there are three real difficulties. One must be able to accurately measure angles of the sky. Okay, so you need some tool for doing that. That's been, a key engineering challenge for hundreds of years. One must know celestial coordinates of stars, so you have to have a celestial map, right? Or these days, there's something on a device. And one must have an accurate clock. This was the biggest challenge for early navigation, because clocks had to be wound up, right? They didn't just continue to run, forever. So what did we learn in this section? We learned how to determine our latitude, right? Just find the altitude of either the sun when it crosses the meridian, or of a special star located at the celestial pole, all right? And longitude, you have to find apparent solar time and compare between that value of two known longitudes. Okay, well, this concludes our lecture for Supplemental Chapter 1. Thank you so much for watching this lecture video.